Now, these equivalence theorems are theorems where usually they are not encountered in an undergraduate course, but they are very useful in computational problems. So, let us look at what equivalence theorems say. So, there is a lot of text, let us go step by step. Okay. So, first we will look at what is called the volume equivalence theorem. Okay. So, let us start with the left part of the slide over here. So, let us say we have some sources and these sources are given by M and J. Okay. Really simple. So, I have some some current source over here M and some current source over here J. Okay. They are nicely radiating, and looking at this blue equation over here, you can tell that there is no object, because which part of this equation tells you that there is no object? Where do the medium properties go into? Epsilon and mu. And what are the values of epsilon and mu here? Mu naught, epsilon naught. That means there is actually no object, so it is vacuum, right. So, this is sitting, these currents are sitting radiating in empty space. So, the fields in empty space or vacuum, they are denoted by the 0 underscript, right. So, denoted by E naught, H naught. Okay. So, the naught on the subscript tells you that there is nothing, it is just the current sources. Okay. These equations we already had a brief glimpse of how to solve them. It was simple, you take curl of first equation, substitute the second equation, you will get a kind of a wave equation, but only difference will be that wave equation will have these current sources. Now, let us make life a little bit more interesting, because real life will have objects. Okay. So, now let us say I place some obstacle over here. Okay. How should I characterize an obstacle or any object? By the medium properties mu and epsilon, which will be a function of space. For example, here there is nothing and here there is the object, right. So, all of that information is captured in epsilon r and mu r. Okay. So, that is why I denoted it as a function of space. So, these equations that are written now are in the presence of a medium. So, apart from epsilon and mu, what is the other change that has happened? Do you notice any other change between these two sets of equations? E has changed, obviously. Once I introduce an object, that object is going to scatter the fields. So, the fields will no longer be E naught, H naught, and now the fields become E and H. Okay. Will the currents change? The current sources will remain the same. I have kept my transmitter still standing out there, right. So, M and J are the same as before. Okay. So, this is the situation that we have. Now, remember that this is what is called a equivalence theorem. So, equivalence means I am going to convert one problem to another kind of problem which may be easier to solve. That is the objective. Okay. So, we will see how that objective is achieved over here. So far it is clear, I started with vacuum, then I went to an obstacle. Now, I do not want to deal with the external current sources M and J, because they may be very complicated to specify. So, the natural thing that I could do is I can take these two sets of equations and subtract them. So, if I subtract them, the advantage is what vanishes? M and J go away, right. So, if I subtract these two equations, what happens is I will get a minus j omega. So, mu naught H naught from the first term, this will be mu H, because I have subtracted 2 from 1, okay, and minus mu naught H naught, okay, the M terms vanished. I can do the same thing. For the second set of equations involving curl of H. So, I am going to get a j omega epsilon E minus epsilon naught E naught. Okay. Really simple manipulation so far. Okay. The beauty of these two equations is that you only have, you do not have any current sources, you just have the fields and the material properties, okay, which I know. Now, this is a good time to introduce one concept. There is a quantity called as the scattered field. You have all heard this word, scattered field. So, what is the scattered field defined as? So, the difference between the electric field in the presence of object and absence of object, right. So, this term over here is defined as the scattered electric field. Okay. So, the word makes sense. Scattered field means the field scattered by the object. I do not want to include the incident field that was already there. So, I subtract off E naught. Okay. So, that is what is the scattered electric field. Similarly, I can take the difference in the magnetic field with and without object, and that difference I will call as the HS, S for scattered, right. So, we will call this scattered.
Suppose we have two objects, will this work?
If there can be as many objects in this problem, it does not matter. All I have to do is include it into epsilon r as a function of space. Epsilon r can be any complicated function, does not matter. Okay. So, I can have one other object over here, no problem. I just have to include that in the definition of epsilon r. Okay. So, this is very general. Even the number of sources can be as many, it does not matter, they all cancel off. Is that fine? Okay. So far we have not actually solved anything, we have just eliminated sources. So, what further can we do with this? So, let us have a look at that. So, I have rewritten the equation from the previous slide over here, right. So, the difference in the electric field incident and total is, this is the scattered field as I already mentioned, and this is what we already had. Okay. So, let us try to do a little bit more algebra on this to bring it into a convenient form. Okay. So, E s I have written as E minus E naught, right. So, what I can do is this term over here, okay, H naught, what I can write H naught as can I write H naught in this form, right. The total field, okay, if that is not clear, we can say that the total field H is the sum of H naught plus H s. So, it says that H naught can be written as H minus H s. Sure. So, this term over here can be simplified as minus j omega mu H minus mu naught H minus H s. Right.
Here mu and H are not function of R.
They are. I have just so mu and so mu over here, I am being lazy over here, mu is still a function of R. Okay. Mu naught is of course a constant. So, in shorthand notation I am just writing it as mu, but they are all functions of space. Okay. There is no need to be giving special treatment to mu or epsilon, they are all functions of space. Okay. And what I can do now is I can combine the H terms. Right. So, I can get mu minus mu naught H plus mu naught H s. Okay, very good. I can repeat the same algebra for the second equation also, right. So, I will write this as minus j omega epsilon E, I leave it as it is, okay, and minus epsilon naught E minus E s in this case. Right. Again I can combine the epsilon minus epsilon naught terms into a E, and I will get a okay. Now, to make our life a little bit more simpler, let us define yet another term over here just to simplify the math. Okay. So, this term over here that you see, right, it is a longish term. So, let us what we can do is we can define something called a equivalent current. And what is this equivalent current? Simply j omega mu minus mu naught times H. Okay. So, this term over here I have put into M equivalent. Okay. I have not solved any problem, I am just rewriting these terms. Similarly, the J equivalent term over here will be written as, so this term over here. Okay. Yeah.
Suppose we eliminate the total field.
We will see. Okay. Alright, so now when we combine these equations, so what is the first equation? So let's call this equation 1 over here. So equation 1 will become, so the first term over here will become minus m equivalent, okay, minus j omega mu naught hs, right. The second term becomes, what do I have over here, minus j and I have a minus j omega epsilon naught es, okay. So let's see, I have a feeling I'm missing a minus, there's an extra minus sign over here, right. So if I look at these equations, yeah, right. So there was this was a plus sign over here, right. So there should not be any minus sign, so we'll keep this plus over here, yeah. Okay, that was a mistake of a minus sign, no problem. Now when you look at these equations, what do they look like? They look like original Maxwell's equations, in which case when there is an object or when there is no object? No object, right. So this is but what have we had to pay as a price? We have had to now introduce some now new equivalent currents, right. But the price here okay. So this volume equivalence principle, what now we can actually have a statement of what it is. What have we done? We started with an object over here, okay, and we started with these sets of equations. As a result of some algebra, I have reduced it down to these sets of equations, which are about sources radiating in free space, right. Mu naught epsilon naught is there, free space. So what I have done is I have replaced this entire obstacle by a set of equivalent volume sources, right. So these m and j, these are sources, okay. So as we will see later on in the course, these kinds of equations, the ones in vacuum, are simpler to solve than these kinds of equations where epsilon is a function of space. So I have not actually solved the problem, I have just converted it into a form that is easier to look at, okay. So once again I want to say, look at the definition of the equivalent current that I have. The definition of the equivalent current contains something which I don't know. I know, let's say j omega mu minus mu naught I know, but I don't know h, I don't know the total field. Similarly for j equivalent I know omega epsilon, but this one, the electric field, I don't know. So I have not actually solved the problem, I have just transferred the problem into m equivalent and j equivalent, okay. So the reason for this will become sort of clear as we go along in this course, but this is a popular way of replacing an object by current sources, magnetic and electric, okay. Remember, this is an equivalent problem, this does not physically exist, there aren't physically current sources sitting in space. I am mathematically thinking of them as it's the same, the solution is the same, because I used these same equations, all I did was add, subtract and things like that, right. So this is the volume equivalence theorem, right. Okay, so this was one of the equivalence theorems. The second equivalence theorem is called the surface equivalence principle, okay. So surface equivalence principles, as you can, the word suggests, I have to now think of the interface between two objects, okay. So there is some normal over here, let us say E1 H1 and E2 H2, okay.
Isn't that H2 minus H1 positive Js?
Again, yeah, the mistake here in the minus sign, this should be plus Js, okay. So let's start with the real problem, the physical problem. Like earlier we started with the physical problem and then we converted it to an equivalent problem. So, what is the physical problem over here? So, I have some current sources over here J and M, okay, and they are radiating in some volume. Okay. So, let us take a hypothetical surface. This surface does not actually exist, I have just mathematically drawn a box, okay, and let us say this is overall, this is the domain that I am interested in. Okay. So, we will call this region 1. So, let us call this V1, let us call this V2. Okay. So, let us play a small game. Let us put one observer over here, okay, and there is another observer over here. Okay. Now, what are the properties of these observers? It is a strange game. This guy, observer 2, can walk around anywhere in volume 2, but cannot walk into volume 1, and observer 1 over here vice versa, can walk in volume 1, but cannot cross over into volume 2. Okay. So, this is, we will call this the real problem. Right. Now, this dotted surface which I have shown you over here, it is a hypothetical surface, it does not actually exist, I have just drawn it, right. So, what do you expect of the fields across the boundary? It will be the same, because I have just drawn a line in air, right. The fields will be continuous across this hypothetical surface. So, when I look at, if I ask observer 2, okay, observer 2 has access to which of these quantities? E2, right. E1 the observer cannot cross over, right. So, if I ask the observer what is n cross E2 for you, he will say okay, n cross E2 for me will be equal to, he will say, hey observer 1, tell me what is the value of E1 on your side. Okay. So, he will write that over here. So, he will write n cross E1, this has come from the other observer, and some neutral referee is required to tell them what is the, is there any magnetic current over there, okay, because this magnetic current is on the, is a pure surface current, it does not, it is not either here nor there, it is exactly on the boundary, right. So, they are told okay, there is there a magnetic current in this hypothetical situation? Will there be? No, right, because it is in thin air. I just made a line in air and said okay, what is the current over here? There is no current, it is free space, there is no current hanging out there, how will there be, right. I just drew a line in air. So, this will be written as plus 0. Okay. So, observer 2 has access to this n cross E2, and observer 1 has access to this, and they say okay fine, they compare n cross E2, n cross E1, what do you expect the answers to be? They will agree, boundary conditions, even though I have created a hypothetical surface, boundary conditions should still be valid. So, they will agree, no problem. Now, we will play a small, we will play yet another game. Okay. So, the game is to sort of make a fool of observer 2, okay, in a way that observer 2 does not know. So, what we do is, let us take the same situation over here, observer 2 remains over here, cannot walk into volume 1, this is V2 and this is V1. Okay. What I do is, so here the fields were EH and EH 2 2 1 1. Here what I do is, I set the fields equal to 0. Remember, this is now a equivalent problem. Okay, it is not a physical problem. The physical problem was here, this is a math problem. So, let us play along with this game. The current sources are here. Okay. Now, actually we need not worry about the current sources over here. I am setting the fields over here E comma H equal to 0 0, that is what observer 1 is going to report. Observer 1 is going to play a little bit of mischief. Observer 1 is going to say fields are 0 inside. Okay. So, observer 2 asks the same question. Okay. He says okay, value of my field over here n cross E2, E2 he has access to. Now, he is asking the observer 1, hey what is the field inside? Okay. Observer 1 being mischief monger says oh, the field inside is 0. Okay. So, the field inside is 0. Okay. to save the is there any way to save the situation and still be truthful to physics? Observer 1 is fixed, I am going to report 0 fields. Is there any way to fix this situation such that observer 2 does not know that anything different happened? Exactly. So, if I look at the boundary conditions over here, what is these two are being fixed by observer 1 and observer 2. So, where is the remaining gap? It is in this term over here. Okay. So, if I introduce a mathematical current which is equal to, so if I introduce, so this will be, so Ms, okay. Ms in this case was 0, right, this was Ms. I introduce a new Ms, and what should I set as the value of this Ms? Right. So, supposing I set its value equal to minus n cross E1. Okay. So, observer 1 set the fields equal to 0, that is all right. I saved the situation by introducing a mathematical, remember this is a mathematical current over here, which is equal to this. So, now this hypothetical surface has a current Ms. Similarly, to save the other boundary condition, I will have to introduce a current Js. So, if I did this trick, will observer 2 know any difference? Observer 2 will not know any difference. Observer 2 walks around everywhere inside this volume 2, and at the boundary it just verifies n cross E2, is it equal to what it was earlier? Answer is going to be yes, because I have put this hypothetical current over here, MSJS. Okay. So, the boundary conditions are satisfied, right. What was there earlier is there now. So, the fields inside this volume and this volume are the same by uniqueness theorem, because E tan has been specified and it is the same in both cases, field will be same in both cases. So, observer 2 did not know what happened, but just see what is, if you look at the overall picture, what have I done? I have punched out one volume and replaced it by 0 fields, okay, and set of equivalent surface currents. Okay. So, object is replaced okay. So, again this can be useful if, for example, I want to reduce the area of my computation. I do not want to compute the fields everywhere in V1 plus V2. If I can remove V1, the small price I have to pay is the surface fields on this. So, they will become the new unknowns, but what I have done is I have punctured out some volume over here. So, these are this is the sort of reasoning behind equivalence principles. The volume equivalence, we saw that the object was replaced by volume currents J and M, as we saw, J equivalent, M equivalent, and in the surface equivalence principle I replaced the object by tangential surface currents. Okay. So, again this will seem a little bit abstract right now, that why are we doing this, but when we begin to take the first method in computational electromagnetics, which are integral equation methods, it will become very, very useful having done this. Okay. So, one example I can give you is this object over here. It may have some very complicated epsilon r, right. So, I do not have to deal with it by doing something like this, by excluding this volume. Okay. But
So you remove J and H and you make the surface current. Is what you do?
I removed the field E and H inside the thing. I do not have to worry about these currents over here, because the role of these currents finally is to produce the fields E and H.
Yeah, exactly.
Yeah. Right. So, this sort of brings us to an end of the two main equivalence principles that we used. By the way, this particular surface equivalence principle that I told you has goes by the name of Love's equivalence theorem. There are other possible variations of this. You can imagine that since this game that I am playing, I have to keep n cross E2. So, what I did is I put all the fields 0 and everything was absorbed into the current, but I can think of some other contribution. and come up with some other equivalence principle, right? And there are several in the literature. So, in the handouts that I will give you, you can look at these other situations. What is the main objective? As I mentioned once again earlier, we want to reduce pain in calculations. So, we will construct these equivalence principles such that the problem becomes easier to solve. Okay. So, that is the idea behind the surface equivalence principle. Okay. So, to sort of summarize this module, we started with Maxwell's equations and boundary conditions, looked at the power, and these two were sort of advanced concepts in electromagnetics. Okay. So, you can look at chapter 1 and 7. So, chapter 1 of Balanis will talk about topics 1, 2 and 3, and chapter 7 of Balanis will tell you about equivalence theorems and uniqueness theorems. Okay. It's a very nice readable book. Please have a read through it.